Hello everybody. So we're going to start talking about how we evaluate limits analytically. Now this does go along with the conversation piece that I had given you, which is a worksheet that you should be looking at as you're going through these. But let's start off with some basic rules. The first thing we're going to have to know is that there's going to be three different tactics that we're going to have to take. And the first one is the easiest, is that if f of x is a well-behaved function, and we've been looking at well-behaved functions when we've been looking at polynomials, if we have a well-behaved function, then a limit can be evaluated by direct substitution. Right? So the very first thing we always want to start out with, if we have a particular function, is that can we just directly substitute into the function with the value of x at that point for the function and get the same limit as though the value of the function itself is that point? The answer is usually yes, if we have a nice well-behaved function. And here's an example of a well-behaved function, y equals 3. Now this goes along with our first basic property, which says this: if you take the limit as x approaches some number c of a constant function, like y equals 3, whatever b is, the limit as x approaches c of b is just b. And to show this, let's talk about the function y equals 3, which is exactly that kind of function. And I let x approach negative 2. So here's the point at x equals negative 2, and the question we might have is that, visually speaking, we can see what's going to happen. What happens as x gets close to negative 2, either from the left or the right? Once we're in the neighborhood of x equals negative 2, that is, what value do we actually approach? Well, since the y value is 3 for every single value of x, then we say that limit must be 3. And so as an illustration of our first rule, we say that the limit as x approaches negative 2, in this particular example, of the function 3 will just be 3. All right, not too bad. There's two other properties right here. This second property says that, well, if we have a really basic function like y equals x, the limit as x approaches c of that function x will be equal to c. And that this is a well-behaved function is easy to see if we take a look at the function itself. Here we are. Let's look at y equals x. On the function y equals x, let's let x approach 4. So here's 4. And what would we say? Well, the limit, it looks like, as x approaches 4 of the function y equals x would be equal to 4, because as we get into the x neighborhood near 4, at every point of x, the y value also approaches 4 from above and below, and in a very well-behaved way. I don't think many functions are more well-behaved than y equals x. So this is an example of our second property. Our third property says that the limit as x approaches some number c of x raised to any nth power, as long as n is a real number, is equal to c raised to that nth power. For example, let's take a look at our function y equals x cubed. This is an example of this kind of function, and we might ask the question, what is the limit as x approaches 2 of the function x cubed? So we go onto our graph right here, we can see exactly what's got to happen. As x approaches 2, that is, once we let x get into the neighborhood of 2, gets close to 2, as x gets close to 2, the y value appears to approach 8 from above or below. Well, in this property, that's exactly what we're saying. The limit as x approaches 2 of x cubed is equal to 2 cubed, and so that limit itself is equal to 8. And so this is the way that we would frame it. The limit as x approaches 2 of x cubed is 8.